Volcanic regions scattered around the planet have always sparked curiosity and fear. Since the earliest civilizations, phenomena related to eruptions have prompted mystical and religious explanations. With the advancement of science, we have come to better understand the internal processes that culminate in explosions of lava, ash, and gases. Even so, reliably predicting eruptions remains a constant challenge. Millions of people live in areas exposed to active volcanoes, and any failure or delay in monitoring can result in human, social, and economic losses on a large scale. Historically, methods for observing volcanoes have included seismic stations to detect tremors, devices that measure ground tilt, tilt meters, and analysis of gases emitted from fissures or fumaroles. In many cases, these systems detect variations that precede eruptions, but it is not uncommon for volcanoes to behave unpredictably, making decision-making and disaster prevention more difficult. In this context, researchers and engineers have been searching for solutions that enhance the ability to detect subtle signs and respond quickly to changes inside the Earth. It is in this scenario that a new sensor emerges, designed to predict eruptions more efficiently. It can detect changes in gas composition almost in real time. The big difference lies in its sensitivity and the way it processes data. While previous technologies often stored raw information for later analysis in laboratories, this sensor is already part of the on-site interpretation, highlighting what may be important for volcanic surveillance. The integrated pre-processing significantly reduces the time between detecting a potential risk signal and alerting authorities. Instead of overloading communication networks with data that would later need to be analyzed, the sensor sends only events considered relevant, speeding up the work of researchers. This approach also helps reduce telecommunication infrastructure costs, as not everything needs to be transmitted. With faster and higher quality analysis, there's an opportunity to activate emergency protocols in advance, possibly saving lives and protecting resources. The development of the sensor combines knowledge from engineering, geophysics, geology, and other disciplines. To function reliably, the so-called precursor signals of eruptions were studied. In many volcanoes, the presence of repetitive microtremors indicates increased pressure or magma movement. In others, changes in the concentration of certain gases suggest significant alterations in the magma chamber. There are also cases where deformations in the terrain appear as clues. The ground expands or contracts as internal stresses vary. The sensor integrates these readings into a single device, capable of identifying potentially dangerous patterns. However, installing and maintaining this type of equipment in volcanic areas is not easy. Many volcanoes are located in hard-to-reach places with extreme weather. Acid rain, strong winds, volcanic ash, and high temperatures create a harsh environment for electronic components. To overcome this, designers adopted corrosion-resistant metal alloys, robust designs to withstand impacts, and special protections against soot and debris. In addition, the issue of power supply must be resolved. In many of these locations, there is no access to a conventional power grid. The solution often involves solar panels, long-lasting batteries, or, in specific situations, self-sufficient generators. It's worth mentioning that the sensor brings additional benefits beyond the immediate prediction of eruptions. With it, it's possible to study volcanic behavior during long periods of apparent calm, collecting data that help define normal parameters for each volcano. This helps prevent false alarms, since if a detected change falls within the natural variation range, there's no reason for panic. It also creates a historical archive of readings, which can be compared with older data and serve as a foundation for increasingly accurate predictive algorithms. Another fundamental aspect is the social impact. Volcanic activity doesn't affect only isolated regions. There are large urban centers near active volcanoes, as well as tourist hubs that showcase the beauty and cultural value of these landscapes. When eruptions strike unexpectedly, they can cause severe structural damage and human losses. In an ideal world, communities would be prepared to act as soon as warning signs are received. For that to happen, the local population must have at least a basic understanding of how the monitoring system works and trust the responsible authorities. Clear communication of risks, evacuation drills, and education on what to do in an emergency are essential components. In tourist areas, the sensor can help assess the risk of keeping visitors in volcanic zones. When readings indicate unusual activity, authorities can restrict access to the volcano, prepare exit routes, and alert the hospitality network. Although this might temporarily reduce the tourist flow, it prevents tragedies and potentially greater long-term losses. In extreme cases, an orderly evacuation allows people to leave safely, infrastructure to be protected, and the resumption of activities to be done in a planned way. Each volcano behaves differently since geological conditions vary greatly from one place to another. Some volcanoes have lava that flows relatively calmly, damaging specific areas, while others erupt violently, launching ash and incandescent rocks into the atmosphere. The sensor is configured according to these specificities. In effusive lava volcanoes, for example, it may be a priority to detect pressure buildup that precedes magma overflow. In more explosive structures, changes in seismic patterns and gas composition may be the main focus. The device's flexibility, therefore, is crucial for it to adapt to different types of volcanoes. To test the sensor's efficiency, research teams often install prototypes on laboratory volcanoes, those considered active but accessible. In these areas, it's possible to compare the sensor's readings with data from traditional seismographs, satellite imagery, and field reports. When tremors or small eruptions occur, the data collected help fine-tune detection parameters, reduce errors, and improve the hardware. After this testing phase, installation can be expanded to more dangerous volcanoes or areas with greater safety demands. The benefits extend to the post-eruption period. Many volcanoes remain unstable, releasing secondary lava flows or ash that can form lahars during heavy rains. The sensor continues its surveillance even after the main event, allowing warnings about new risks. This way, authorities can plan the reconstruction of affected areas without exposing themselves to imminent threats. The same applies to reopening roads and allowing residents to return to their homes. The comparative analysis of data provided by sensors installed on different volcanoes around the world also allows for the creation of comprehensive mathematical models. Some researchers study the relationship between high-frequency seismicity and the release of certain gases as an indicator of a likely eruption within days. Others correlate the waveform of microtremors with the type of magma rising. Thus, the accumulated knowledge about various parameters and their combinations enriches the forecasting outlook, bringing increasingly greater accuracy to diagnostics. There is also the prospect of continuous evolution in onboard technology. In the near future, even more sensitive versions may be able to detect electromagnetic signatures or small changes in the ground's electrical conductivity. Researchers are studying possible magnetic fields generated by moving magma, which could be yet another indicator to monitor. Everything suggests that new discoveries will add to current readings of vibration, gases, and deformations, making the sensor even more comprehensive. The analysis algorithms, in turn, are likely to become more sophisticated, using deep neural networks trained to recognize pre-eruption patterns more quickly and efficiently. It's important to emphasize that eruption prediction is not an exact science. Even with excellent sensors, uncertainties remain. A volcano can simulate an eruption, emit signals considered worrisome, and then suddenly return to a dormant state without releasing lava or ash. Still, this kind of false positive is preferable to failing to issue a timely warning in real danger situations. The sensor aims to increase accuracy, but does not promise absolute precision. The decision to evacuate or issue a public alert lies with the authorities, who must consider both the technical readings and the broader socioeconomic and logistical context. From the perspective of populations living in risk zones, the presence of a sensor network brings a sense of reassurance, as there is trust that potential signs of dangerous activity won't go unnoticed. On the other hand, complacency must be avoided, since nature remains unpredictable and emergencies can unfold in a matter of moments. From this point of view, technology is a key element of protection, but it does not replace the need for urban planning, well-defined escape routes, and awareness campaigns on how to act when an alert is issued. It's worth remembering that volcanoes play a fundamental role in Earth's geological formation and even in the fertility of many regions. Where volcanic ash is deposited, the soil often becomes enriched with nutrients, benefiting agriculture. That's why millions of people live on slopes and in valleys near volcanoes, taking advantage of the natural benefits these areas offer. However, this proximity brings constant danger, and the adoption of advanced forecasting and alert systems emerges as a way to balance life alongside active geological forces. In some cases, a volcanic eruption has an immediate global impact, especially when the ash cloud interferes with air routes. Since airplanes cannot safely fly through dense ash clouds, airports shut down and supply chains can face disruptions. In this way, local monitoring of a specific volcano becomes relevant to airlines and governments far away, as it affects international traffic. The sensor, by providing reliable and near-instantaneous data, helps guide decisions about rerouting flights or suspending them when necessary. Moreover, well-structured alert systems prevent the chaos that arises when an eruption is discovered too late. The immediate reaction to an unexpected risk is often disorganized, causing traffic jams, supply crises, and frequently widespread panic. The population without guidance is at greater risk of accidents and becoming isolated. When advance warning is available, even if just by a few hours, it becomes possible to organize a coordinated evacuation, set up temporary shelters, stock supplies and medicine, and relocate people with limited mobility. These procedures can make the difference between a controlled crisis and a humanitarian catastrophe. Another important point is how the sensor connects to larger planetary monitoring systems. Networks for monitoring earthquakes, tsunamis, hurricanes, and other natural threats already exist. The trend is to integrate these networks and create a global database, allowing scientists worldwide to share information. This way, any abnormal change detected in a remote volcano can be quickly analyzed by experts from different countries, speeding up validation and response. This kind of cooperation reduces costs and strengthens the overall capacity for defense against extreme events. Basic research on volcanism itself also benefits. With detailed instrumentation, a deeper understanding is gained of magma dynamics underground, the relationship between geological stress and explosive eruptions, and how external factors, such as climate, can influence internal activity. Each volcano monitored by a high-precision sensor becomes a field of study for undergraduates, graduate students, and researchers working on related topics such as plate tectonics, geochemistry, and geodynamics. In this way, scientific knowledge advances, and the practical outcomes benefit not only the local community, but humanity as a whole. It's undeniable that we are witnessing a major breakthrough. Even though it's not infallible, the sensor introduces an additional layer of safety in places where the risk of eruption is a daily reality. By combining precise measurements, sophisticated algorithms, and robust communication infrastructure, it creates a kind of radar that scans for signals not always noticeable to the naked eye or with traditional equipment. The evolution of this tool, along with the constant refinement of analytical techniques, tends to make eruption forecasting less dependent on expert intuition and more grounded in concrete evidence. In summary, the new sensor designed for volcanic eruption prediction represents a major technological and scientific leap. It consolidates decades of research, combining hardware robustness, software sophistication, and integration with other monitoring methods. Although there are still barriers to its widespread adoption, mainly financial and logistical, the path taken points to continuous improvement in how we deal with active volcanoes. At-risk communities, civil protection systems, and researchers will increasingly be able to rely on trustworthy information, gaining time to prepare, and avoiding, whenever possible, the devastating impact of an unexpected eruption. After all, the planet is dynamic, shaped by intense forces working beneath our feet. Volcanoes will continue to exist, periodically releasing lava, ash, and gases into the atmosphere. However, with this type of sensor, humanity moves forward in its ability to better understand the warnings the Earth gives before unleashing its stored energy. It's an investment in knowledge, in safety, and in a more harmonious coexistence with nature itself.